Yeah, good afternoon, everyone. Today, let's start now. So, today I will recall what Professor has told in this week 4. First, some few topics. One is L0 norm. He introduced what is L0 norm. So, L0 norm, suppose there is a vector x. X is a vector which belongs to n-dimensional vector. So, then what is the L0 norm? L0 norm can be written as number of non-zero elements in the vector x. So suppose there is a vector x equal to so here what should be the L0 norm? If the L0 norm should be number of non-zero elements, so here the L0 norm will be 3. Yeah, one more question is that is the L0 norm is really a norm? The answer is no. So L0 norm is not really a norm actually. Why? Because to satisfy a function to be norm, we have three conditions. I have mentioned in the first class. So the first condition should be non-negativity property. Here this condition is satisfied. So the first condition is non-negativity. Uh, non-negativity. So this is satisfied. But so then the second condition was the homogeneous property. So that means uh, so C of x, that should be equal to mod C. Okay, so this condition should be satisfied. But let's check now. So uh, so suppose let C is equals to some 3. Okay, so for this example, so here so for this example, what should be the Cx? Cx will be uh, 36090. Okay, so then what should be the L0 norm? Now, what is how many non-zero elements are there? Only three elements are there, so three only. But this is not as same as uh, this thing. Uh, 3 into, so this is not same as 9. See, that is same as C into normal. So this is not same. So that's why this homogeneous property is not satisfied. So homogeneity doesn't hold here. So that's why. So uh, so so LGO norm is not actually a norm actually. So that's why we have the formula. This LP norm is equal to this summation of mod xi power p 1 upon p. So so this is only applicable for p greater than equals to 1. Now the second topic is okay. So one more application of this L0 norm is the is in compressed sensing. Okay, so application compressive sensing. The or the topic is the sparse signal recovery. So, what is sparse signal recovery? So, sparse is so suppose there is a vector x. X is called sparse. If x has x has so many zeros in x actually. Suppose so, what is the sparse vector? Sparse vector is a vector which has so many zeros, many zeros. So, suppose there is a 100 cross 1 vector. Out of 100 cross 1 vector, suppose 95 zeros are there. Okay, zeros are 95 zeros. Sorry. Hmm. So zeros, all zeros, 95 zeros are there, and all non-zero elements. Some one is there, which is five. Five non-zero elements are there. So this is a sparse vector, we can say, because only five are non-zero elements. So it's called a sparse vector. And then what is the sparsity? One term is there. What is sparsity? Sparsity is how many non-zero elements are there. So here sparsity is five only. Five is the non-zero elements out of 100. Out of 100, only five is the non-zero elements. So in the sparse signal recovery, this L0 norm means number of non-zero elements. So that means so for the sparse vector, L0 norm should be very small. I mean, we need to minimize the L0 norm to uh, to recover the sparse vector. Now the second topic is some then he the professor mentioned some special some properties some which will be helpful in the later context. So suppose so first one is so one is this one. Suppose there is a matrix A matrix. So A is a matrix M cross P, and B is a matrix. B is a matrix P cross M. Okay, so then AB will be M cross M, and BA will be uh, P cross P. Then he mentioned that this I this is the identity matrix with dimension M cross M dimension. So I plus AB is the determinant. Determinant of I plus AB is same as determinant of I plus BA. Okay, so these two determinants are same. Okay, he has proved it using similarity transform maybe. Yeah, so this can be proved by normal determinant formula also. You can prove it. Uh, then so in the second properties that if A is positive definite, then A inverse will also be positive definite. So the proof is very simple. He also mentioned if A is positive definite means all the eigenvalues will be uh, more than greater than equal to 0. So all the eigenvalues greater than equal to 0. So sorry, not greater than equal to greater than 0. Positive definite means greater than 0. So okay, so that means 1 by lambda is also more than 0. So uh, and okay, so that's why this A inverse is also positive definite. Okay, so then the third property is that AB and BA have the same eigenvalue. So suppose this A is a matrix, uh, A is a matrix n cross n. So A and B both are the n cross n matrix. So then both have the same eigenvalues. So that means their character. So he has also proved it using the characteristic equation. So he has shown that the characteristic equation for AB and BA. So this is not A minus B. This is AB. So the characteristic equation for uh, AB and BA both will be same. So that means so this lambda I minus AB is same determinant of this. This is the characteristic polynomial is same as lambda I minus BA. Then uh, one more thing is that AB is similar to BA. Eigenvalues of unitary matrix have unit magnitude. So suppose there is a unitary matrix U n cross n matrix. So then U Hermitian U is same as U Hermitian is same as identity matrix n. Now, and let lambda x be eigenpair. I mean eigenvalue, eigenvector pair. Okay, so eigenvalue, then eigenvector pair of x of u. Then what is this? This u x equal to lambda x means x not equal to 0. Then u Hermitian ux. U Hermitian ux equal to lambda u Hermitian x. Okay, so then u Hermitian u is identity matrix. So this is becomes x itself, the same as, and u Hermitian has the uh, eigenvalue lambda star. So okay, and then you can multiply it with convention. Okay, so then we can multiply it by x Hermitian also. Then it will be x Hermitian. So then this becomes mod of lambda square equal to 1. There is one also easy proof also. Okay, this means summation. This is the identity matrix. So this is the proof. And then so that means suppose so there is a matrix unit. If the matrix is unitary, then the all the eigenvalues will. So suppose this is a complex plane. This is the real and this is the imaginary. So all the eigenvalues will be in this unit circle. So this radius is 1. So then the one more property is told that is so L1 norm is less than equal to root n L2 norm. So he has proved it using Cauchy-Schwarz inequality. So he has already proved it. So I will not go through it using Cauchy-Schwarz. Then one more property, it is x2 norm. X2 norm is more than equal to x infinite norm. So um, so that also he has proved actually. So ultimately using this f and g, so these last two properties, then we can write down uh, x1 norm is 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 uh, uh, is greatest among all the norms, and then L2 norm, uh, and then the lowest norm is infinite norm. He has mentioned that suppose x is a vector, then this is also a convex set. So there is a set S. S takes all the vector x such that x1, x2 is more than equal to 1, x1 is greater than equal to 0, and x2 is greater than equal to 0. So this is also convex set because he has mentioned that this is the intersection of all alpha greater than 0, all x vectors such that alpha square x2 plus some x1 is greater than equal to 2 alpha. This is the intersection of infinite half spaces. So that means it's a convex set. Suppose there is a random variable x. So x is a random variable, and it has the probability mass function. So sorry. So the probabilities are like this actually. So suppose x takes the values as a1 to an. Okay. So this is the uh, values of x can take actually. So a1 to an, and corresponding to each and every value there is a probability that is suppose p1 for this is the pn. So that means pi is equal to probability of x is equal to a I. Okay, so let us take this thing, and then the set is which takes all the p vectors. So p vector is equal to p1, p2, pn transpose. So suppose this is a vector. So all the p vectors such that this expectation of x is upper and lower bounded by uh, alpha and betas. So is this set convex? So, so this is also a convex set. Okay, because why this is a convex set? So he has also mentioned that so this expectation of x is equal to summation of equal to 1 to n pi and then ai. Okay, so this is same as we can write down some a1 to an. This is a vector, row vector, and one more is this is a column vector. This is equals to, suppose this is a transpose, we can write down. So this is a transpose, this is p, and alpha is less than equal to expectation of x less than equal to beta. That means this alpha is less than equal to a transpose p less than equal to beta, and this is the half space. So sorry. So then so this is a, so so this, there are two half spaces. Then from this we can write down what a transpose p is less than equal to beta one, and second one is alpha is more than equal to a transpose p, then negative half space. So a transpose p is less than equal to minus alpha. So there are two half spaces, and it's the intersection of two half spaces. So it's a convex set. So now let us take one more set that is equal to all the p's, such that probability of x greater than alpha is than equal to beta. So this is also a convex set. He has mentioned that why this is convex. All thing, everything he has. And one more, this is also a convex set P such that expectation of x square. So now so all the properties are done. Now we'll go to some definition. So one more topic, that is a convex function. Convex function, definition of convex function I have mentioned in some, maybe last to last class. So the definition of convex function is that, so fx is said to be convex function. Fx is, so x can be vector said to be convex function if this theta f of theta x plus 1 minus theta y is less than equal to theta f of x plus 1 minus theta f of y. So for all x, y, and theta belongs to 0, 1. So this is the definition of convex function. Okay, so Professor has already mentioned that one example of convex function is that exponential. So example, the exponential. For a greater than equal to 0. Thank you. Sorry. So this should be a less than 0. Then it is 8 power x. And if a function is convex, so f of x suppose is a convex function, then minus f of x is said to be concave function, where this less than equal to becomes greater than equal to. Now, how to check the convexity? So that is the main problem. So how to check convexity? So suppose for the scalar case, scalar case means the function. Sorry, this x vector. So this is scalar. Let us take. So fx y equals to fx. Okay, so this is a scalar function. So professor has already told that. So for this case, this d2 if dx2, if this is greater than equal to 0, then it's a convex function. Now for vector case, so for vector case, this x is not a vector now actually. For this case, suppose y equal to fx. Okay. Function is scalar, y is taking scalar, y is scalar, but x is not scalar. Okay. So for this case, derivative will be defined as like this actually. So one first order derivative is defined as using gradient actually. So no need to write down this. So it's this is the gradient. So this is the n cross 1 vector. So then this will also be n cross 1 vector, and uh, we'll differentiate y or f with respect to each element in x. So that means del x1 f, then del f del x2. So this is the gradient. Then what is the Hessian? So Hessian, so it's a double derivative. So that means we need to we need to differentiate this gradient of fx again. So then that means and so this is a vector. So and we need to differentiate this vector with respect to another vector x. So that means that will become a matrix n cross n matrix, and so first element will be double derivative of del x1 2, and then second will be So ijth element can be written as tail differentiating f with respect to I and j. So okay, and the condition is that earlier it was greater than equal to 0. Now it's a matrix. So matrix greater than equal to 0 means matrix should be positive definite. So that means this should be greater than equal to 0. Positive semi definite. Okay. So then on application he has also mentioned. Yeah, the application is that MIMO data detection. MIMO means multiple input, multiple output. So that means suppose this is a vector. Vector is n cross 1 vector, and H is a matrix. Okay, so let's change this dimension. So suppose this is a n cross 1 vector, and H is a matrix m cross n, and X is a vector n cross 1 plus n. So this is the receiver noise. This is the m cross 1 noise. Now we need to estimate X using known using y comma h to be known. So we know y the measurements and h is the channel matrix. So the channel matrix and measurements we know. Now how to estimate x. So so the least the problem is using the least square here solved. So the least square problem is that least square problem is that so square will be least actually. So that means square of what? That means square of the distance between y and hx. So minimizing the distance. So we'll search over all the x and we'll minimize the distance between y and hx. Okay. So this is a least square problem, and the solution will be he has solved using this convexity concept, and the solution will be H Hermitian H x equal to H Hermitian y. So this is the solution. So this is called as normal equations. Normal equations. And if H is full rank, that means H Hermitian H, that is also full rank. So that means this H Hermitian H is non-singular or invertible. Then X hat. So suppose this is X hat actually. So it satisfies this condition. This is the X hat. X hat equal to H Hermitian H inverse H Hermitian Y. Okay, so this is the least square problem. And this thing can be written pseudo inverse actually. This is called a pseudo inverse. So that is written as h dagger, let us take. So then x hat will be equal to h dagger y. Okay, and in MATLAB there is one command, this pseudo inverse. There, so there is this inbuilt function h admission, h inverse, h admission. So then we'll solve some sample problem now. So this is all done for the so that's all for all the topics. So now for some sample problems. X tilde is a vector, and let's take x n cross 1, then x n plus 1. So first one is vector and second element is a scalar. So it's a n plus 1 cross 1 vector. Okay. So then let this, then so S is a set. S takes all those x tilde such that this norm of x is less than equal to x n plus 1. So the question is, this represents first one is option is that norm cone, sphere, the ellipsoid, hyperplane. Okay, so the question is very simple. So it's a straightforward MCQ question. So it should be a norm cone.
Rom-com.
So the L infinity norm wall for the set of two-dimensional vectors. So this is the uh, question. So options are, so this is also I mean professor has also mentioned this thing. So this is very simple. So answer should be, I will not give the option. So if the answer is the, it's a so L infinite norm, right? So it's a square. So it's a square where this all the sides are parallel to x and y axis. And then number 3 is that expectation of x square is equal to a. Okay, okay. So let me write down in different way. Is a set of vectors such that is a is a what is a half space. So why half space? So this already has professor has already mentioned. So I can also write down. So the half space is so this expectation of x square. Okay. So expectation of x square is equal to summation of uh, pi, where pi is the probability of each element, and this pi, and then ai is the ai square. So this is the expectation of x square. Then so this also can be written as a1 square, a2 square, then an square, p1, p2, pn. So then this can be taken as another vector actually. So let us take this another vector as some v vector. Okay, so this is v into p. So this is the p vector. So this is the v into p. So now expectation of x square is less than equal to some a. Okay, so that means, so suppose this is a v transpose. So that means this v transpose p is less than equal to a. So this is the equation of half space. So that's why. Now fourth question. Suppose this is a region V, all X such that so is a so it's a definition. So is a polyhedron. So then the next question is that L1 norm ball. So L1 norm ball is a tilted square. And L in L2 norm ball is a circle. So these are for two dimensional. Then the next question is f of x1 comma x2, where this let us take this vector x1 and x2 as a, so let us take this vector has two elements only, x1 and x2. Okay, so now so this the function is there defined like this actually, is equal to a1 x1 plus a2 x2 minus tau log of x1 comma x2. So is this a convex function or not? The solution is this. Yes, the criteria to check the convexity is using the Hessian for the vector case. So this is a vector case. So we need to apply the Hessian concept. But if you this x is scalar, then we can apply double derivative case concept. But it's a vector. So now finding the Hessian. So Hessian means Hessian means this. This is the Hessian. So each one will be 2 cross 2. Two elements are there, x1 and x2. So we need to derivative f with respect to x1, double derivative with respect to x1, and then uh, so now let's do these things. So first is derivative with respect to x1 only. So this is the a1 minus tau log of x1 x2. So this is x1 and x2 multiplication. So minus tau divided by x1 x2 into x2. Similarly this, then what should be the with respect to x1 only, so minus, so minus, then it will be minus tau by x1 square, so tau by x1 square, and then this. So del f del x2 is a2, correct. This is independent of x1, so that's why. So now okay. So, so what should be the Hessian? So first element will be tau by x1 square, 0, 0, tau by x2 square. Okay. So now 2 cross 2 matrix. So the matrix will be positive semi-definite to become for the fx to be convex. So positive semi-definite means all the eigenvalues will be positive semi-definite. So how? So suppose if A is positive, definite, then x admission x is greater than equal to 0. Okay, so then that means, so now for all x, okay, so then we can put x as an eigenvector also. So putting x equal to eigenvector of A. So x admission, so Ax equal to lambda x greater than equal to 0. So that means uh, uh, lambda mod of x square greater than equal to 0. Now eigenvector can't be non-zero. Eigenvector is non-zero actually. So that means the mod of x is non-zero. So that means lambda is greater than equal to. So this is the uh, so then all the eigenvalues of a positive semi-different matrix would be uh, should be positive, should be non-negative. So so that means let us check here. So here the eigenvalues are this. So it's a diagonal matrix. So eigenvalues will be the diagonal elements will be the eigenvalues. So that means tau by x1 square and tau by x2 square. Okay, so the reverse is also true actually. If a matrix is positive semi-definite, then all the eigenvalues will be positive, will be non-negative, and the reverse is also true actually. So that means so if lambda greater than equal to 0, all the eigenvalues is positive, then this x summation ax will also be greater than equal to 0. Then a will be positive, uh, is positive semi-definite. Okay, so this also can be proved. So that means we need to show that this eigenvalues are non-negative or not. We need to check those things, that thing actually. So x1 square and x2 squares are positive, but tau we don't know, tau is positive or no negative, we don't know. So that means so Asian is positive semi-definite if tau is greater than equal to 0, correct? So so fx is convex if tau greater than equal to 0. Okay. So this is the case. Now for the next case, so for this, suppose we have one constant optimization problem. So consider the optimization problem as follows. So minimizing something x, minimizing with respect to x, fx, where fx is mentioned as above actually. So this fx, yeah, this fx. So we need to minimize fx. So so what should be the constant set? So such that so the set should be x1. So x1 greater than equal to 0, x2 greater than equal to 0, and x1 plus x2 is 1. Okay. So for this case, uh, so for this case, so this is not the subject. So suppose this is the subject to. Okay. So um, so these are the set omega, and this is the function. Okay. So now is this a convex optimization problem? So uh, for the convex optimization problem, the two conditions are there. The function which is to be minimized or which is to be optimized, so that should be a convex function. So f of x, we need to check f of x is a convex function. We have already checked that, so it's a convex function. And number two is that the set omega, which is a constant set actually. So omega is a convex set. Okay, so in the last maybe last to last class, I have shown that this for this case this itself a convex set actually. So this itself I have taken that time as a problem. Then this is a convex set actually. So here omega is a convex set is satisfied and fx is also convex set. Okay. So it's a convex optimization problem. This is a convex optimization problem. Okay. But why do you need to check this is a convex optimization problem or not? Because we have some general theorem for convex optimization problem. Okay, then we can apply those things here also in this case, and then we can optimize it easily. Then, okay, so that's all for the problems. So now I will introduce something, some inequalities which will be helpful now later actually. So there are three inequalities, many inequalities are there. First inequalities are some one is the Markov's inequality, which will be helpful. I mean, it will be applied later. Quality Markov's inequality. So suppose x is a non-negative random variable. So x is a non-negative random variable means it will take only the non-negative values. Non-negative random variable. So if x is a non-negative random variable, uh, then we can write down, and epsilon is greater than equal to 0, we can write down. Okay, so and if suppose epsilon is a small number which is only greater than 0, not equal to, then we can write down this probability of x, sorry, probability of x greater than equal to epsilon is less than equal to expectation of x divided by epsilon. So the proof is as follows. So so x is a non-negative random variable. So what should be the expectation of x? So 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 it will go to 0 to infinite x and fx. So where this fx of x is the PDF, probability density function, PDF x. Okay. So as x is a non-negative random variable, then we can write down from 0 to infinite. So that's why. So then and epsilon is more than 0. So then we can 0 to epsilon x fx of x dx plus epsilon to infinite. Okay. So so here inside this x is also positive, and this fx of x, this is also positive. So this is greater than equal to, all are positive. So then it is more than, if I omit one integral. So okay, and okay, now and x is more than epsilon. Okay, so then there is more than this epsilon to infinity, epsilon into f of x, because x is more than epsilon. So I am putting the lowest value of x. So that is same as epsilon into x. Now, what is the probability of x greater than equal to epsilon? That is the fx of x dx, the epsilon to infinity. Okay. So that means it's a epsilon probability of x greater than equal to epsilon. So means the good. Okay. And then one more inequality is there. Second one is the Chebyshev inequality. So, this probability of square. Okay, so how where this sigma square is the variance of x. So where sigma square is the variance of x. Okay, the Chebyshev inequality, and second one. So it's a corollary of Markov inequality, and third one is the Jensen's inequality. This is very applicable here. Jensen's inequality. Suppose if fx is a convex function, an expectation of, sorry, expectation of f of x is less than, sorry, so f of expectation of x is less than equal to expectation of fx. Okay, so this is Jensen's inequality. So what is this? This is suppose f of x. So expectation of x equal to pi, pi or question. Okay, and professor will maybe uh, uh, derive the proof in the next class, maybe in the week fifth, maybe Jensen's inequality. So this will be applicable in this context. Yeah, correct. So yeah, that's all for the day. So if you have any question, you can ask me. Yeah, hello. Yeah, one asked. what is the use of hub space? So hub space will be useful in every, I mean, many optimization problems. Suppose there is in wireless communication. Uh, okay, so in so this hub space and ellipsoidal model, those will be applicable for the uh, this constant sets actually. So suppose in many cases this hub space, so I can say, so in the in wireless communication, suppose there are uh, many powers are there. Okay, so transmit powers are there. Okay, so then so then we can write down this summation of pi is equal to p total. Okay, and one more thing. Okay, so for the hub space, it's should be some a transpose p is less than equal to something. Okay, something b, something is there. So so it's similar kind of thing actually. So it will be applicable in those cases. Uh, okay, and for that case, this optimization problem. So as the hub space is convex set, then we can use the convex optimization problem. Uh, then we can optimize it actually. So maybe those things will be taught in the later classes. So you will understand how these hub spaces will be applicable. So this is the very important space, that is hub space actually. So yeah, in the later context you will know actually. An ellipsoidal model is same actually. So for the ellipsoidal model, suppose we have some channel estimation or some estimation, okay, and then some estimation is there, x hat, and the true value is there x actually. So then this is less than equal to something a something. In that context, it will be uh, applicable. And professor has mentioned maybe in his class that for the ellipsoidal model, so suppose this is ellipsoidal model, and then this is the estimated center is the estimated value, and then estimation, and then so it's some channel estimation problem he has mentioned, and then actual estimation, sorry, actual channel will be lie in this region. I mean everywhere that can lie. So our job is to minimize the ellipsoidal volume or something he has mentioned. So yeah, those are the application. Yeah, now let's conclude the class and let's summarize what I taught today. So this so I have revised this topics what professor has already taught. So first one is L0 norm, and then so what is the definition of L0 norm? And this is the application of L0 norm is to recover the sparse signal. And then second, so then he has mentioned some important properties. So those are some those I have mentioned here also, and those will be useful later. And this L1 norm is more than equal to L2 norm, then that is also more than equal to infinite norm. That's also, and then all this so there is some sets we need to show that these are the um, convex set or not. So okay, and then what is the convex function? And then in the problem in the sample problems I have defined what is the convex optimization problem. So for the convex optimization problem, the function should be convex, what should be minimized, and the constant set will also be convex, and convexity check is there. So for the scalar case, we need to double derivative the function, and we need to show that it is more than equal to 0. And for the vector case, we need to show that the Hessian is positive definite, positive semi-definite, and the application is there. So Professor has told that Professor has applied this to detect the MIMO detection problem, and so he mentioned that this is a least square problem is there to minimizing the distance between y and hx for all x, and so the solution is this is a least square solution, and then I have mentioned some sample problems. Uh, so this is okay, some sample problems, and then then I have taken one function fx, which is a vector function, and I've shown that this is a positive semi-definite matrix. The Hessian is positive semi-definite, and the problem is the function is convex function. And then I have taken one more constant set, and we are the problem is to minimize fx over the constant set. And so as the constant set is also convex and function is also convex, so that this optimization problem is also convex. And then I have mentioned some inequalities. So one is Markov's inequality, then Chebyshev's inequality, then Jensen's inequality. So these inequalities will be helpful later in the later context. So that's all for the day, and have a happy weekend.